everybody's back from. Hope everybody back from break. We're gonna resume class. Before break, we were talking about internal structure of the central processing unit. We have the arithmetic logic unit, which tell to perform arithmetic and logic operations. Then we have the shifter, which is a component of the arithmetic logic unit. That is there to perform bitwise shift operation on data. Like we have done the shift right or the shift left. So this shifter is there to perform the shift bitwise operations. And we have the complementer. This helps to perform complement of binary numbers, which will help to perform addition instead of subtraction to make the hardware much simple. We have registers. We have registers, general purpose registers, as we have seen, special registers with special purpose, and we have the control unit, which is there to manage all the operations being performed by our processor. We have register organization, user visible registers. These help programmers to reduce main memory access by efficiently using register storage to temporarily store result. We have the control and status register, which are being used by the control unit as well as the operating system to manage processor operations and program execution. We have to discuss user visible register. We have 4 categories. We have general purpose register, data registers, address, and conditional code. Now, let's talk about control and the status registers. These are not visible to the users. Some of them can be accessed by machine instruction in control or operating system mode. We have these 4 different registers, which are very important to the execution of the instruction. We have the PC, program counter. These contain the address of the instruction that need to be fetched. PC contain the next address of the next instruction to be fetched. We have instruction register, IR. When the instruction has been fetched, it needs to be stored in the instruction register. Then we have MAR, memory address register, which contain the address of the location in the memory. Memory address register contain the address of the location in the memory. Now we have MBR, memory buffer register, which contain a weight of data to be written to the memory. This acts as a buffer between the processor and the memory to store a weight that needs to be written to the memory. Now, we have these 4 important registers for instruction execution. We have program counter, instruction register, memory address register, and memory buffer register. Now, which register contain the next instruction to be fetched from the memory? Which register contain the next instruction, the address of the next instruction to be fetched in the memory? Hello? Class 6, number 4. Which register contain the address of the next instruction to be fetched from the memory? Huh? Absent. Number 4, absent. Class 6, number 4, absent. Not there. Class 6, number 4. Not there. Okay, class 1, number 5. Class 6, number 5, absent. So what is the register which contain the address of the next instruction to be fetched from the memory? So the register which contains the address of the instruction to be fetched from the memory is PC, program counter. So it's very important to know the role of some special registers, because when you are analyzing the results in emulator 8086 register, it will help you to understand why you have got the result, the right result, or the wrong one. Now, we have these 4 important registers for execution of the instruction PC to contain the instruction, the address of the next instruction to be fetched. We have IR instruction register to contain the instruction mostly recently fetched. We have memory address register to contain the address of allocation memory. We have memory buffer register, MBR, to contain a word of the data to be written to the memory. It acts like is a buffer between the processor and the memory. We have example of memory processor register organization. We have data register. We have address registers. We have also program status, program counter, status register. This is for MC600 microprocessor. And we have example of microprocessor register organization for our 8086 microprocessor, which is in the middle. This is B. We have learned about the organization of this 8086 microprocessor. So it's quite easy to have a general idea about processor register organization for a specific register, which can help you to understand the organization of other types of registers. For example, you see we have general purpose register here, pointer and index, but here we see for MC 68000, we have data register, address register, and program status. For 800386, we have general purpose registers as for 8086 microprocessor, but they are extended accumulator register, extended base register, counter register, data register. So it's better we have learned 8086 microprocessor organizations, processor register organization. To give us idea about other registers is organization. Now, instruction cycle. We have 2 important steps. We have fetch to read the next instruction from the memory. We have execute. It has first to decode the instruction fetched from the memory, then perform the operation. Now, we have the start. This means start of the instruction. Okay? Start of the instruction. So once it is started from here, it needed to fetch the next instruction from the memory. Once the instruction has been fetched from the memory, our microprocessor needs first to decode the instruction fetched from the memory, then execute the instruction. And so on and so forth. Once the execution of the first instruction has been done, our microprocessor will start again to fetch the next instruction, then decode the instruction, then execute the instruction when there is no heart. If there is a heart, that means it won't affect any register, but it means that the CPU is in what we call idle mode, waiting for the next instruction to continue the operation. Hello? Two steps of instruction cycle. We have fetch and execute. During the fetch cycle of instruction, microprocessor leads the instruction to be executed from the memory. Once that instruction is fetched from the memory, it decodes the opcode to understand what it does mean, then execute the instruction. When there is no heart, the microprocessor will start the next instruction by fetching the next instruction to be executed from the memory, then execute it. When there is a heart, this is very important, but it won't affect any flash, but the microprocessor needs to be in what we call idle mode. Idle mode. Idle mode. This means the processor needs to wait for some time to start the execution of the next instruction. So it has to wait for the next command to continue the operation. It will be in idle mode for a while. Now we have 40 memory format from Institute for Advanced Studies. It has 40 bits, and we have left instruction, which is 20 bits, and right instruction, which is also 20 bits, which divide into opcode and address code. So we have opcode and we have the address. Now, fetch cycle, the program counter holds the address of the next instruction to be fetched, and the processor fetch instruction from the memory location pointed by the PC. The PC will contain the address of the next instruction to be fetched by the microprocessor. Then it has to increment the PC unless told otherwise. We have the instruction loaded into IR, instruction register, and the processor interprets instruction and perform required actions. During the execute cycles, we have data which has to be transferred from the CPU and the memory, main memory, and we have also data transferred between the CPU or input-output module. Then there is data processing, which means the processor needed to perform arithmetic or logic operation on the data, fetch the data. Then there is also control. That means there is alteration of the sequence of the operations. Now, we have a simple example for program execution. We have a 8-bit data, and we have integer format. For the instruction format, it is also a 16-bit data, which contain opcode of 4 bits, and the rest is for the address. We have the program counter, address of the next instruction, and we have the instruction register, which is the instruction being executed, and we have the accumulator register to add to accumulator from the memory. Now, we have a simple example of the program execution. The PC is there to contain the next instruction, the address of the next instruction to be fetched from the memory. Step number one, we have memory addresses. These are memory addresses, 300, 301, and we have here the content of each memory addresses. And we have the PC, which is set to be in 300 memory location. And we have the content of the 300 memory location, which is loaded in instruction register. In step number two, the PC has been incremented by 1 to point to the next memory address to be fetched. Then we have the instruction register, which has loaded the content of memory location 300. Then the accumulator register is loaded by the content at memory location 940. In step number 3, the pointer program counter pointed to 301 memory location. Then the content at 300 memory location has been loaded into instruction register. Then we have to add the content from the accumulator register and the content at the memory location, which is stored at 941. Then we get a 5. So we see that the program counter is again incremented in step number 5 to be pointed to the next instruction to be fetched in the memory, that is 302. Then we have the content at this memory location, which is loaded into the instruction register. Now we have 2941. Then we see that the content of the accumulator register has been updated because of the addition that has been done here. Now, here, if you try to see these 4 first bit of the content in the memory location 300 is to load, because it's 1 here. 1 here means load accumulator from the memory. Now, 3 here means add to the accumulator from the memory. That's here, we have done the addition, 3 plus 3 plus 2, because here we have got a 2 to add the content from accumulator to accumulator from the memory. Then you see we have got a simple example of program execution. So let's talk about indirect cycle. Indirect cycle. The execution of an instruction may involve 1 or more operands in the memory, each which require a memory access. So we have seen that each instruction works on data, so the microprocessor needed to get access to the memory. Now, for example, we have, if it is indirect addressing, we have the additional memory accesses that are required. Now, we fetch data from, we fetch the instruction from the memory. Then if the instruction has been got, we can execute. If there is indirect cycle, indirect addressing, multiple memory accesses are required to complete the instruction. Now, instruction cycle state diagram. Fetch instruction from the memory. Once the instruction has fetched from the memory, we needed to identify operands. So first identify the operands once the instruction fetch has been done. Fetch input operands from the memory. For example, if there is indirect addressing mode, we need to fetch input operand from the memory. When it is register-based operand, we don't need to require fetching input from the memory because the operation is based on the content stored in the register. Then we execute we decode the opcode to understand, to interpret what it does mean to the microprocessor. Then execute the whole instruction, store the result in the memory if it is required, or store it into the register, depending on which kind of operation the microprocessor is being executed. So we have instruction fetch the instruction from the memory. We have also to fetch instruction operations, to fetch operands. We have also to fetch operands from the memory if we are using indirect memory, indirect addressing mode. We need to fetch operand from the memory. But when we are using, for example, register addressing, fetching operand from the memory is not required. So we have the data flow. We have seen these four important registers: program counter. We have seen instruction register. We have seen memory buffer register, which acts as a buffer between the memory and the processor. We have seen the control, which manages the operation being executed by our memory, our microprocessor. So this memory buffer register is important as a buffer between the main memory here, which is random access memory. We're going to talk about the memory during chapter number 3. We talk about the different types of memory. So this main memory, most of the time, is the random access memory. We have different buses: address bus to transit address, data bus, and the control bus as well. Now, instruction pipeline. Pipeline technique is very important because it allows the microprocessor to execute multiple instructions at the same time. I mean multiple instructions in the same clock cycle. If there is no pipeline technique, that means one instruction has to be executed one after another, which will take longer for the microprocessor to complete all the instructions that it has on its hand. So which means the pipeline is there to speed up the execution of the instruction by executing many instructions in the same clock cycle. Now we have instruction fetch. That is for the first instruction. We have instruction decode, execute, then get the result. For a simplified view of that, when there is a fetch of the first instruction, it will go for decode. Then the next instruction will be in fetching a cycle of the instruction, and so on and so forth. So which means the microprocessor will be able to execute multiple instructions in the same clock cycle. You see fetching, wait, then instruction, execute, wait. So this will cause too many wait. So to solve this problem, instruction pipeline has been introduced to allow the microprocessor to execute multiple instructions at the same time. Here you see fetch instruction, then wait, execute instruction, wait for the next address to be fetched from the memory. So which will take longer for the microprocessor to complete the instructions. Now, to solve this issue, pipeline technique has been introduced. In computer system to allow multiple instructions to be done in the same clock cycle. Now we have the same a clock cycle here. We have logic for stage 1, we have logic for stage 2, and we have logic for stage number 3. That means the startup of the next instruction does not need to wait the first instruction to be done unless it is what we call dependent instruction. Now we have timing diagram for instruction pipeline operation. Fetch instruction leads the next expect instruction into a buffer. Decode the instruction, DI, determine the opcode of the instruction. Calculate operands, CO, calculate the effective operand for the fetch the instruction, and then fetch operands. FO, we need to fetch each operand from the memory. For example, if we are using the indirect addressing mode. Then execute the instruction, perform the indicated operation, then store the result, if any. Then write operand, store the result in the memory. So this is the timing for instruction pipeline. Now, a simple example of pipeline. A simple example of pipeline, we have time. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is like we have time. These are clock cycles. So this is instruction number 1. For instruction number 1, we have instruction fetch here. Hello? Instruction number 1, let's say this is the addition. It is in instruction fetch stage. Once the instruction number 1 started the instruction decode, the instruction number 2, we start instruction fetch. Now, this means during the time number 2, our instruction number 1 is in instruction decoding state, whereas our instruction number 2 is in instruction fetch stage. Now, during the time number 3, that is the clock cycle number 3, calculate operand, CO, calculate operand. Our instruction number 1 will be in calculate operand stage, whereas our instruction number 2 will be in decoding stage. Now, instruction number 3 doesn't need to wait these two instructions to be done. When our instruction number 2 is in instruction decode, our instruction number 3 will be in instruction fetch. Now we have time number 4, that is clock cycle number 4. We have FO, fetch operands. Now our instruction number 1, during the time number 4, will be in FO, fetch operand. Then our instruction number 2 will be in calculate operand. Then our instruction number 3 will be in next stage, that will be decoding instruction. Then comes instruction number 4. Instruction number 4 will be in instruction fetch. That is the first stage. Now, during the time number 5, we have AE, execution of the instruction for our instruction number 1. Then the instruction number 2, we move to the next stage, which is fetch operand. Our instruction number 3 will be in calculate operand. And our instruction number 4 will be in decoding instruction. Then start instruction number 5. Instruction fetch. Then during the time number 6 will be write O, which is write or store the result into the memory. Write operand, write the result, store the result to the memory. Now, write operand. This is the end of the first instruction, and during this instruction, this time number 6, our instruction number 2 will be in execution stage, and instruction number 3 will be in the next instruction stage, which is F4. Instruction number 4 will be in the next stage, which will be calculate operand. Our instruction number 5 will be in instruction decoding. Then instruction number 6 we start FI here. Now the instruction number 2 we go into write operand in time 7. Our instruction number 3 will be in execution. Our instruction number 4 will be fetch operand. Instruction number 5 will be in calculate operand. Instruction number 6 will be DI equals operand. Then instruction number 7 will start fetching instruction and so on and so on. So this allows our microprocessor to execute multiple instructions during the same clock cycle, during the same time. Question? Huh? Question? Question? So, the FF of a conditional branch of instruction pipeline, we can also have a branch penalty. This is something that we're going to talk next class. Then we're going to also talk about the pipeline hazard. A pipeline hazard occurs when the pipeline or some portion of the pipeline must wait because of the condition, don't permit to continue the execution. Like there is resource hazard, they need to have access to the same resource, memory for example, or data hazard when one instruction needs to wait the first instruction to be done before continuing its operation. This we call dependent instruction. We also have control hazard. We're going to talk this in our next class. Questions? Hello? Questions? No? No questions? How many minutes left? 10. Questions about instruction types, instruction sets, or about processor organizations, or any other topics that we talked the last time? Luego meio, oyo. Questions? Yo encima. Meio. Luego meio, oyo. So questions? Those who are sitting backside, hello, I want you to sit somewhere here. Last law. Okay, if you don't, you want to get the paper? That's fine. 10 minutes, please. Distribute the paper here, okay? The last law, you need to move somewhere here. As I said before, You don't still remember? At the beginning of the class, I said it, okay? Don't complain. Otherwise, you won't get a paper. No, distribute the paper inside. Last law, you won't get a paper. I say it. You need to sit in front. Everybody has got a paper? Extra papers? Thank you. Everybody has got a paper? So I didn't ask you to talk. Everybody has got a paper? Extra papers? Thank you. I don't. Question number 1 includes different questions. First, you need to comment on each line code, then answer the content of the and the above blog. Question? You don't. On each line code, then what is the content of base register and accumulator register after the execution of the program. Three more minutes. I wanted to remind everybody, question number 1 include 2 different questions. The first one, comment on each line code. The second one, after the execution of the program, what will be the content of BX and DX registers? So 2 different questions. Hey, what is wrong? Everybody has done. I see all side. So pass your paper to your classmate who is sitting at your right. I want to see all the papers for this law here. I didn't ask anybody to move. Please stay in your places. Only I want the paper to be on this side. Thank you. That's all for this law. That's all for this. Hello. Everybody has submitted their papers? Everybody submitted their paper? Submit paper? Submit. Question number 1. Comment on each line code. I have seen some students who didn't do that, and I repeat many times. Comment on each line code. Shemeis. Okay, that's all for today's class. I'll see you next class.